So thank you for the invitation to this wonderful conference. It's my pleasure to be here. My name is Ioan Pop. I'm a professor jointly between the Karlsruhe Institute of Technology, which is where the research lab is located, and the University of Stuttgart, where I have my teaching duties. And this is a peculiar German format for some professorships, especially those associated to a national lab. And what you might not know from the name is that KIT historically was the university that integrated a national lab, and that's why I fall under this system. So the national lab network in Germany, it's called Helmholtz. It's called the Helmholtz Association. So in our group, we are interested in many aspects of superconducting quantum devices. We are trying to build superconducting qubits, couplers, amplifiers, and even detectors. Because when you have a qubit that is very sensitive to its environment, it's a terrible qubit, but it might be a great detector. Right? So we always try to keep in touch with the detector community to learn from them and basically avoid doing what they are doing. So today I will talk about a modular crosstalk-resilient architecture for superconducting qubits. So it's basically a talk that goes along scaling. The goal here is to scale up. But you will see the way we want to do this is we are not trying to compete with Google or IBM on numbers of qubits. We are trying to break some records, but in quality, let's say, and especially in modularity and crosstalk resilience. So the results that I will be talking about are summarized in these two papers. With you can see the first two authors are the same, Simon and Sören, and then Sören and Simon. And these are back-to-back papers. One is about the type of fluxonium qubit that we used, and the other one is about the architecture that allows us to put three of these. Actually, they're not really fluxonium qubits. They are more in the generalized flux qubit regime. So the superinductor is not that large to call it a fluxonium. And I will talk about that. And then we put three of them in this kind of assembly. You don't see it very well here, but there are actually 5 sapphire chips. You don't see them that well because they're transparent. And each sapphire chip fulfills a role. But what you can see here are the screws. So we attach them with screws. This is very Victorian-like. It's like when you take pipes and you connect them. But I would say that's a good thing because in an academic lab, right? So in an academic lab, you want things to be as modular and as easily replaceable as individual objects as possible, because my students are much happier if I tell them go in the clean room and make 100 qubits and choose the best 2 ones and mount them here. Or if I tell them go in the clean room, make a qubit with 3 qubits and 2 couplers, and they all have to be good, right, in the same chip. Like that's a much, much more difficult job. Okay, so the last thing I want to say on this slide is that this work was supported by one of the large consortia in Germany, QSolid, which is all about scaling gate-based computing, and Abacus, coordinated by Paul, which was about trying to go a little bit into the building hardware for quantum annealing. So this hardware is sitting somewhere in the middle between the two. So superconducting quantum processors are amazing. I think I don't have to explain this to this crowd. We have proofs of scalability for around 100 qubits. We have tasks which have been shown to be faster on quantum computers than on classical supercomputers. And we have the recent results from Google, where they have shown that they go beyond the break-even point in quantum error correction. So these are clearly very exciting times. And I would also like to highlight the recent plans from IBM, which in their recent roadmap, where they are planning to operate 200 logical qubits, and each logical qubit is about 100 physical qubits, 100 something. So in the next 5 years, right? More like four years at this point. And I want to highlight this because it's the first plan for scaling up that I see, which is not obviously ridiculous. Right? Which maybe if you look at this, schematics where you see this is basically a human, and the quantum computer is this entire part here, which is basically the volume of this room, and probably bigger than the volume of the hallway where we have the lunch breaks. So that would be the cryostat, that would be the 50 millikelvin stage, right? That volume. But that's actually not a big problem. As you can see here, all you need is a series of pulse tubes and a series of electronics racks. And it actually does make things easier. Like building a large cryogenic volume makes things easier because the cooling power scales with the area, right? But you gain with the volume. Right? So the scaling is favorable in that direction. So maybe, I mean, I don't know if they will make it, but maybe we will see Shor's algorithms on hundreds of logical qubits by 2030, and that would be amazing, right? That would be clearly another inflection point in the development of our field. So, okay, this is all the good news. Now let's switch to the bad news. So the bad news is that these objects, these superconducting qubits, are quite tricky to fab, not because the structures are very complicated, but because we need them to be very coherent, right? So we need, in the fabrication process, any leftover contamination, any dissipation that we introduce is a big problem, which is a fundamental difference with the semiconductor industry, right? Like in the semiconductor industry, they can build very complicated devices, but they don't care if they are dissipative. Actually, it's even better if they dissipate because dissipation is kind of like acts as a stabilization for semiconductor devices. The second problem, which I already touched on, is modularity. You can easily appreciate the fact that if all of your 100 and something qubits in this processor have to work, that is a very high threshold for success. And the problem is that even when we cool them down and we operate them, sometimes qubits get sick cryogenically. Right? So they are already in the fridge, and then one of them gets sick for various reasons, which are quite interesting physics. But then you don't have a way to exchange it, right? Because everything is in one monolithic architecture. The other problem with monolithic architectures is crosstalk. Right? So trying to suppress crosstalk on chip below 30 dBm, minus 30 dBm, minus 30 dB. It's a very difficult task, and I would say no one knows how to do it. Right? So there are solutions, there are involved technical solutions to go in the minus 30 dB range, but much below that, to reach minus 40, minus 50, I think it's really pushing the boundaries of physics, because the fact that you have metals and substrates shared between qubits, that just means you will have this part per 10,000 crosstalk, whatever you do. Right? So that is a problem. And then, of course, the chip itself is a source of correlated errors. For instance, one of these errors could be coming from an ionizing radiation impact, either from cosmic rays or from local radioactivity, which creates phonons, which are phonon shockwaves, which are then shared with all the junctions, with all the qubits on the substrate, right? And that's Google calls this catastrophic error bursts in this paper, and we have shown in this paper, we have shown that if you go underground in a deep underground lab in Gran Sasso in Italy, you can suppress by a factor of 50 the rate of these events. Google has shown in the recent error correction Nature paper that you can also suppress these error rates by doing very aggressive superconducting gap engineering on chip. So that also works. Nevertheless, even with these mitigation strategies, error bursts, catastrophic error bursts, are still give the saturating point for the error correction code that Google has shown. So this is still an ongoing. There are mitigation strategies, but the problem is still open. All right. So now that we know what the challenges are, let's see what are some of the solutions in the literature. So I'm just going to show you, I will highlight 3 non-monolithic architectures. There are others. These are the 3 that inspired us. So there is the approach from Rigetti, which is to use chiplets and then use flip chip to connect these chiplets. And you have, as for instance here, you have qubit 1, qubit 3, and you have this series of connections through silicon vias. So this is clearly an interesting approach. It's also quite technologically involved. These silicon vias for an academic group, I can tell you, are quite intimidating. Another approach is coming from the Oxford group, where they use these post cavities. You see, this is the post cavity. Then you put the qubit in the middle, and then it's really out of plane. It's really 3-dimensional. And then you have the control at the top. And then you have, basically, it looks like a forest where each tree is one of these readout cavities. And then from the top, you have the control. So this is also quite interesting and also modular. You can exchange the chips. And then there is the approach from Urbana, from Wolfgang Pfaff's group, where they call this Lego-like, which I think it's befitting for. So they have 1 qubit in one qubit and readout module in this copper box, 1 qubit and readout module in this other copper box, and they literally connect them with aluminum superconducting cables. Right? So the cable itself becomes the coupling resonator, like you see it here. And then you can drive these Raman-like transitions to perform 2 qubit gates. So you use the one state of the bus, of the resonator. You just use it as a stepping stone, basically, to drive 2 qubit gates. Now, this is great. This is a very nice architecture, which also offers very high isolation and modularity. I would say one drawback of this is that once you have fixed these frequencies and once you have fixed the design, then your gates are the frequency for your gates are fixed. There's no in situ tunability in this architecture, and this will be one differentiating aspect compared to what the type of 2 qubit gates that I will show you. All right, so these are our 3 inspiration points. So what is our plan? Our plan is to use flip chip. You'll see it's a very low technological depth flip chip. It's basically, by flip chip, I mean a student comes in with a tweezer and flips a chip on top of the other chip. That's our flip chip, okay? And I think for academic groups, that works very well. Now, of course, if you have access to a professional flip chip bonder, great, yeah. that will probably be better. Then it will be cavity-based, so each of our qubits will live in its own clean environment cavity. So it's a one cavity, 1 qubit approach, and it will be Lego-like in the sense that we can change each chip individually. And we'll put them together, so we'll use this, in each cavity we'll have some input-output for the readout, and we'll have some XYZ control through flux lines and through drives. And then we'll couple these cavities by overlapping chips with each other, and we'll have some capacitive extenders there to perform 2 qubit gates. All right, so this is the plan. Now let's start by looking into one cavity. Right? And I would like to thank the previous speakers for already giving very pedagogical talks in which they introduced all the major concepts. So I can probably go pretty quickly through this. So our qubits are dispersively coupled to a readout resonator. So our readout resonator is an inductor and a capacitor. It's harmonic. All the levels are equally spaced. Then we need our qubit. This is this part of the Hamiltonian in blue. This is anharmonic. It can be a transmon. We use transmons, but what we don't like about transmons is their limited anharmonicity. So often what we like to use instead is flux qubits. Right? And I will use the terminology of generalized flux qubit, which can go from the regime of, like, historically the first qubits measured all the way to the fluxonium, where the inductive energy is much, much smaller than the Josephson energy. Okay? So in a flux qubit, as we have seen many times already this morning, you can have a very large enharmonicity. The first transition, because it benefits from this bump in the potential right there at half flux, can be separated by gigahertz, so you can have enharmonicity on the level of gigahertz compared to the other transitions, which become more and more harmonic. Right? So even in the fluxonium, as you go higher and higher in the potential, it does become more and more harmonic because it sees less and less the bumps from the Josephson junction. And the last part is the readout. So this was also discussed. We have this type of coupling, which looks like a longitudinal coupling. It's an illusion. It's actually a transverse coupling, which in the dispersive limit becomes longitudinal. But that's great. It just means that based on the state of our qubit, as you see here, our frequency of the resonator will acquire this chi shift. Okay, that's what this coupling tells us. So we will get some response of the readout resonator in blue when the qubit is in 0, and some response when the qubit in red when the qubit is in 1. And this is how we're going to distinguish our states 0 and 1. And there are many ways to achieve this coupling on a circuit. We will use this shared inductive coupling that you see here. So basically, we are sharing between our readout resonator. You see what happened here? We had readout resonator and qubit, each of them with their own inductors. And now they still have their own inductors, but we do share one inductor in the middle between the readout resonator and the qubit. So that's how we'll get the coupling between them. So let's look at some circuits. So let's build a circuit from bottom up. We start with the Josephson junction. Then we add the flux qubit loop. This is our flux qubit loop. And we add a shunting capacitor. And now we add, okay, so maybe I should stop here to point out that this device already has two modes, actually. It has a very enharmonic mode in which this island and this island charge with opposite signs. Right? So this sends a lot of current through the junction. But there's another mode, because we have another island right here. This is the third island. There's another mode where island 1 and 2 here are synchronized, so there's no current through the junction. But there is a voltage difference compared to this third island. So there's a lot of current going synchronous through these two inductors, right? So you have this mode, the qubit mode, and you have this mode, which is the more harmonic mode. Ideally, if these inductors are perfectly symmetric, actually this is a perfectly harmonic mode. Make sense? This qubit, this resonant. Okay. So we used to call this, for a long time, we used to call this the parasitic mode. And we were quite annoyed by it. And we tried to engineer the device to push it up in frequency and not care about it. And at some point, the student was just like struggling and was suffering. And then we decided, let's embrace the pain. And let's actually make this the readout mode. I mean, why not, right? So if you just introduce a little bit of asymmetry between these two inductors, actually you couple the qubit and this parasitic mode. And now this parasitic mode, you can load it with a little bit of inductance, and you load it with some more capacitance, and now you actually push it down in the range where you want your readout to be. And then you can use it. And this has the advantage that now you have actually suppressed. You have actually removed your parasitic mode, because there's no more parasitic mode. Each mode does something in the device. So it's very economic in some sense. We have 3 islands, so that gives us 2 modes, and we're using both modes. Right? We're engineering them, and we're using both. So this is the qubit mode. Again, this is the readout mode. And the coupling will be given by this asymmetry in the inductors, this delta K. And of course, there are other capacitors. And this capacitor in particular here, this will be useful to couple to the readout lines, to the coaxial line. And these capacitors here, this one and that one, will be useful to couple the qubit to other qubits, to perform 2 qubit gates. All right? This is how it looks like in reality. So you can easily match the two. This is the loop, so this is the loop. In the middle of the loop here, you will see the junction. Each red line here, one red line, another red line here, implements the inductors. So unlike what we've seen in the first few talks, Our inductors are not made with Josephson junction arrays. Our inductors are made with granular aluminum, which is one of these disordered superconductors that Tim has mentioned in his talk. So we can get very similar nanohenry per micron length inductors with granular aluminum. And it has some advantages and some disadvantages, which you will see, compared to junction arrays. But for now, we have chosen to stick with granular aluminum because we really like the advantages. Now, the rest is quite obvious. You see these capacitors. This capacitor is that one. This one is that one, and so on and so forth. And if we look at the fabrication sequence, you can see that there are 3 shadows. So we use 2 shadows for the junction. Okay, sorry, yeah. So we use 2 shadows for the junction right here. And then we do a 0-angle evaporation for granular aluminum, which is in red, which connects then to both of these. Just want to switch back. So maybe just a side comment about granular aluminum, the red wire that you see here. Its microstructure consists of 3 nanometer diameter grains, something like that, which are perfectly crystalline embedded in an amorphous oxide matrix. So due to this structure, it's often modeled as a network of tunnel junctions. And this modeling actually can go quite far. So you can read in this paper from Natasha Maleva from our group back a few years ago. You can see how we construct this Josephson junction array model. And I would say in the last 7 years, we have only done, all of our experiments have only confirmed this model to greater and greater detail. To our surprise, I have to say. It's surprising to see how well this junction array model holds. Good. So now, if you zoom out from this picture, basically you can see what happens below this line, right? So right here, below this line, there's just a big capacitor pad, which is basically the capacitor pad, the coupling pad of the readout mode, which we use to couple to the flip chip, where we have the Purcell filter and the coupling to the coaxial lines. So we have measured quite a few qubits, and we put them on this plot, where we have EJ on this axis, EL on that axis. And now the color encodes the frequency of the qubit. So you see in this range, it's very low frequencies, whitish. In this range, it's quite high frequencies, all the way up to 8 gigahertz. And the box tells us the anharmonicity in gigahertz unit. So this qubit, for instance, had a 1 gigahertz anharmonicity. This one had the 2 gigahertz, and this one had like 5 gigahertz, so almost anharmonicity. So basically, what you can see is that the frequency on this diagonal, when you go up on this diagonal, the frequency goes up, and the anharmonicity goes down. Generally, that's what happens. And this makes sense because the diagonal is basically the plasmon versus fluxon delimitation for separator for this parameter space. So anything that's above this diagonal, basically it's a single well. So we call this the quarton regime. It's a single well which has some modulation due to the cosine potential, which makes it anharmonic, but it starts to look more and more like a transmon qubit. Okay? And anything that's below that line, it's a double well. And then the deeper you are, so the closer you are to this corner, the more into the heavy flux qubit limit you are. So the more your qubit eigenfunctions are given by tunneling under this potential, Josephson potential right here. So can we actually understand now also the coupling? So can we understand our chi? So we have a quantitative model that you can read about in the paper. And basically our circuit model is the tiny circle, the measured chi is the big circle. And this is basically also kind of chronologically, qubit 1, qubit 2, qubit 3, the devices. So you see, in the first few devices, we had some mistakes, and we couldn't get quantitative agreement because the device was not perfectly mapped to our circuit model. But then we figured out how to do things better, and then we could get really well understood devices where the circuit model could perfectly explain the measured chi shift. And also the values are in the range of 1 to 2 gigahertz, which is megahertz, sorry, which is the optimal range for qubit readout. So how does the readout look like? Well, we have our flux qubit coupled to the resonator right here. Then we have to go through a parametric amplifier in order to make sure that the response in the IQ plane, in reflection in our case, the scatter of the response will be given by quantum fluctuations, not by some classical noise. So you see we'll have a pointer state corresponding to state 0, pointer state corresponding to state 1. This corresponds exactly to this phase roll that I already discussed. And the fuzziness corresponds to quantum fluctuations if we use a parametric amplifier. In this case, these are parametric amplifiers fabricated in our group. And when we look at actual data, this is what we see. So in this case, we applied basically we stopped halfway into a Rabi oscillation to have roughly equal populations in 0 and 1, so we can see very clearly these blobs. So we have a signal-to-noise ratio of 3, which means that the circle here shows sigma, so the deviation is 3 sigma between these two blobs. Note that the scale bar is logarithmic here, so you can see also single counts and thousands of counts, right? So this gives us a very good separation fidelity in the range of close to 2 nines, so that's not a problem. But what I really want to highlight here is the fact that we use 85 readout photons in the resonator, and basically almost nothing bad happens, right? Like we have less than 1% excursions outside of the computational space, even though we are driving quite strongly. And this data is integrated 100 or 200 nanoseconds, so it's also quite a fast readout. So we can use this fast readout to perform active state reset. So we have a fast FPGA board. Oh yeah, it's 200 nanoseconds in this case, the readout. So we perform a readout for 200 nanoseconds. We decide very quickly if the qubit is in the excited state or the ground state based on the IQ response. And then if it's not in the target state, we apply a pi pulse, which can be very fast here. I mean, it's 70 nanoseconds here, but it could be much faster. And then we measure again. So, and then we repeat this to have statistics and to have clouds, okay? So if we do that, we can reset to the ground state with a very high accuracy, almost 3 nines. And again, I want to highlight that there's basically nothing. We could see, if there would be some leakage out of the computational state, we would see it, and we do see it, but only 1 part per 10,000, okay, in this case. And then if we do the same for the excited state, we get less fidelity, so we only get 93% for the excited state. We understand where that's coming from. It's the T1 of the qubit, right? So the T1 of the qubit was in the range of 10 microseconds, and then you plug in those numbers, and then you get the 93%. So if we correct for T1, then this is actually also very high. But again, what I want to highlight is that we get a bit more. We can see that there's a bit more scatter here out of the computational space, but still very little. So this is in contrast with transmon qubits, where at this point, we would just see a whole mess. You wouldn't be able to see the qubit state at this point, at this readout power. So that's what we really like about this qubit. What we don't like is the T1. So the T1s are in the range of several microseconds. Sometimes, I mean, we have measured sometimes above 10 microseconds up to, I think, most recently, we don't have the recent points, but we have gone up to 15, 20 microseconds, but not longer than that, right? And we have transmon qubits which can go routinely above 100 microseconds in the lab with the same junctions, same evaporation tool, same everything. So this is a problem, and it's actually, we are not the only ones to notice this. The community has noticed that flux qubits made with disordered superconductors for the superinductor, they are actually suffering from inductive losses. This was also noticed in the former Alibaba group. And that is because the flux qubit is particularly sensitive to inductive losses at half flux. Right? So if you look at the quality factor of the superinductor, it's not bad actually. It's like 10, it's a million, that's not a bad quality factor. But it's nevertheless, this number will limit your qubit T1 at around 10 microseconds. And the magic of junction arrays, why do fluxonium qubits with junction arrays have much longer T1? Well, the magic which is not understood, I'm not complaining, I'm just saying it's not understood, is that this Q inductive in junction arrays is 10 to the power 8 or 10 to the power 9. And that's a bit like a gift from nature, which we should not complain about, but I think we should understand and try to see what is happening in junction arrays that's so good, and maybe then try to replicate that in disordered superconductors. Okay. So that's an open scientific question at this point. So I think I will conclude with this part on the single qubit at this point. So our summary of the generalized flux qubit with granular aluminum is, I can split it in two parts. We like that we have a very localized coupling with very low crosstalk to other elements on the chip because it's all inductive coupling. We have a minimal mode structure. So basically we have a device with free islands, 2 modes. We use both modes. All the other modes, because granular aluminum has a very high plasma frequency, terahertz, all the other modes are very, very high in frequency, so we can forget about them for now. And we have very low leakage outside of the computational state, not only during gates, but also during readout. So we can have a quantum non-demolishing readout. The problem, as I mentioned, is coherence. It's likely limited by Graal, and I think it's an interesting fundamental physics question, why? Okay, so that's work in progress. Now, let me move on and try to couple several of these qubits together. So this is what we're going to do. We're going to have qubit 1 here, qubit 2 here, and then we'll have a third qubit here, which we'll just call coupler. That's what we will do. So this is how the sample looks like in reality. So we have individual enclosures, 3 of them. We have coaxial ports, which come on the side. Each enclosure has its own coaxial ports. Then we have the control chips, which are wire bonded to these coaxial ports. And the control chips are very easy. They don't have junctions, right? So the success rate for the control chips is very high. The control chips have a wire bonding pad, and they have Purcell filters, which are, you can engineer them and you can really fabricate them with high reproducibility. So basically once you wire bond one of these control chips, you don't really touch it again. That's why we screw them down, to make sure that they stay put. And then we have our qubit chips, which are flip chipped on top of the control chips, and they are not screwed in. They are attached with vacuum grease, thermalized with vacuum grease here and there, such that we can easily swap them. So if we measure this assembly and this qubit we don't like, come in with a tweezer and swap it in for a new qubit, cool down. So it's a very fast turnaround sample holder. Basically, it's very adapted to sandboxing. So if you want to test many things quickly and only change one parameter at a time, this architecture allows you to do that. So this is how it looks like in reality. Of course, it's not. It's a bit more messy, but not too messy, I would say. So the bottom chip is the black-green. The top chip is the light green. And you can see that they are overlapping. And these are the 2 capacitor pads overlapping right here in the center. You have 1 capacitor pad on the bottom for the for the control chip, and you have another capacitor pad on the top for the qubit chip, and right in the center you can see the qubit loop, actually. And then these long lines that you see here with coupler pads at the end, these are our capacitive extenders to couple to qubits in the next enclosures. Make sense? Feel free to interrupt me if something is not clear. This is a photograph of the device. And now, if we look at the coupler chip will look very similar. The coupler chip will be, again, another qubit. So it's our inductively coupled qubit resonator system that you can see here with capacitive extenders and a fast flux bias line right here. So we will use this fast flux bias line to modulate the frequency of this qubit later on. Now we put a cap on top of everything. We use these walls to also hold the chips in place and pin them down. And we use 3 coils, 3 solenoids, to apply some low frequency, basically some DC flux offsets to our flux qubits. And that's it. And this is how it looks like now in reality. So now I zoomed into this picture so you can actually see 1 control chip here. Then you see the qubit chip on top of it. The qubit chip overlaps right here with the coupler chip in the middle. And the coupler chip also overlaps with the second qubit chip here, which then overlaps right here with the control chip. Okay, so this is 5 chips in this assembly. And basically each line here, each readout line here is coupled to one of our parametric amplifiers, and it goes to a single shot readout. So we have single shot readout of everything. Single shot readout of qubits and of the coupler, and you'll see why that's really cool. So these are the three qubits. Again, the middle one is just a coupler. So qubit 1, qubit 3. Qubit 1 we don't touch, we park it at the sweet spot. Qubit 3 we bias it, we want to bias it on resonance with qubit 1. By the way, all of the measurements that I will show you are with the qubits exactly on resonance. So the only reason why we have to change the flux on this qubit is because we are not accurate enough, let's say, with the fab. The fab is not predictable enough to actually fabricate these two qubits exactly identical. If we could do that, that would be great. So then we would only need to learn how to fabricate one qubit. That's it. One qubit frequency. That's it. And you could extend it forever. You will see why we can do that in a moment. And the short reason is because they don't talk to each other. The crosstalk is very small. And then we have the coupler, which has to be tuned. When the coupler is on resonance with the qubits, then we say it's on. When it's off resonance at some point, then we will say it's off. Okay? And there are better off points than others, as you will see. So we show isolation by driving through one single port, the qubit associated to that, well, actually the resonator associated to that port and the neighboring one. And then we measure measurement-induced dephasing. We look at the measurement-induced dephasing, and we can see that, of course, versus at low powers, the first qubit that dephases is qubit 3, of course, because it's closest. And then if we want to dephase qubit blue, qubit 1, we actually have to go 64 dB higher in power. Right? That's a pretty good isolation. And we can confirm this also with qubit measurements. So now we do Rabi oscillations on the two qubits on resonance in the same time. And this is what we see. So if we drive both of them through port 3, you see we can drive very fast Rabi oscillations very quickly on qubit 3, and then we have to go to pretty high power to get some very modest Rabi frequency on qubit 1, and again the isolation is 60 dB. And as I mentioned, we can actually drive both of them together. These are acquired in the same time. These are 2D plots of the Rabi oscillations. You see this is the qubit 3, qubit 1, and qubit 1, as you can see, only oscillates versus this voltage, and qubit 3 only oscillates versus that voltage. So we don't have spectator errors in this architecture down to the level of part per million, which is really nice. It means you can really forget about this problem. So how about ZZ crosstalk? Well, what we can do is that we can apply a pi pulse or no pi pulse on port 3, and then look at the frequency of qubit 1. And then what you see is a very small shift between pi pulse and no pi pulse. And this shift is some hundreds of hertz. So the ZZ crosstalk is also very, very small, as you would expect from these objects. So great. So we have very isolated objects in different boxes, not surprisingly maybe, but now can we actually couple them? Can we do two qubit gates? Okay. So this is the coupling that we can measure. So the effective G13 versus the detuning. And I would like to highlight that we understand this quantitatively thanks to our collaborator with the group of Juanjo. And I would say the only downside is that this G, we would like it to be not 2 megahertz effectively, but 20. And I think we know how to do that. We just have to increase it by a factor of 10, and that will give us the optimal coupling. And the other point I want to highlight is that here we get perfect suppression, and that's because an interference effect at this point where you can couple directly through the qubit, or you can actually couple through a parasitic capacitance between them. And here the coupling really goes to 0. So you can get very high on-off ratio by changing the coupler by 100 megahertz or so. So not crazy. Great. And you could do baseband. Swaps between these qubits. Basically, bring the coupler in resonance, wait for a while, vacuum Rabi, go back. This is what Google is doing, for instance. So that's one way to do it. But I would like to show you here a new way of doing two qubit gates. And this is based on Landau-Zinner-Stückel-Berg-Marana interference. So So I always call it Landau-Zenner Stückelberg, but then, or Landau-Zenner interference. But then people, as you read more, you realize that more people have thought about it in the same time. So then, to be fair to everyone, we just call it LZSM. And the idea is very simple. Again, the qubits are perfectly fixed. So you see this qubit is perfectly on resonance with that qubit. And the only thing that we are doing is that we are modulating the coupler. And basically, we are crossing, if this is the resonance frequency of the qubits, basically, we are crossing it with the coupler up and down. So we apply a flux modulation, and we go up and down. And every time we cross this Landau-Zenner transition, right, there is a probability that the state of one qubit goes into the coupler, and then when it comes back, that it is given back to the other qubit. So this probability will have a phase, and basically what we expect to see is an interference pattern based on the phase acquired above and below the Landau-Zenner transition. So when you repeat this a few times and you acquire some phase, you can really think about it as an optical setup where you go through beam splitters. Okay? And at the end, you will measure an interference. So this is really a beam splitter interferometer. And what we see is interference. So I'll just tell you that you only have to look at one row, the experiment, let's say, because the theory reproduces almost perfectly the experiment. So let's just look at the top row. So we start with qubit 1 in the excited state. That's why it's orange. Okay, so orange is excited state from single shot measurement, right? So from blobs, basically. So there's no doubt about that. And then you see that most of the time the qubit 1 remains orange as a function of drive amplitude and frequency. But at some points, its state goes to qubit 2, goes to the coupler and to qubit 2. Okay, so if we look, so if we zoom in right there in this area, we are looking for some line which exists here, but not in the coupler. Right? That's basically what we are trying to achieve, and we can find many of these points. I think that what I'm trying to say here is that this gate can work at many frequencies and many amplitudes. There are many combinations. So it's not fixed, like I was saying about the setup developed by Wolfgang Pfaff. This is in situ tunable. You can choose your operating point. And now this is, again, these are measurements. Both plots here are measurements. This is not theory. And what we do is that we start with the qubit in state 1, coupler in 0 and qubit 2 in 0, and then we start to drive our gate. And you can see that the frequency of the gate is arbitrary. We just chose 25 megahertz. It's a nice number, right? And you can make it work at any frequency that you want. You can actually make it work. Right? There will be a combination of amplitude and frequency that works. So if you want to use your favorite frequency, please do. Okay, in this case at 25 megahertz, you can see versus time that we get these oscillations where the state from qubit 1, when we are actually right on resonance with the interference, disappears. It actually first goes to the coupler. You see it appearing here. But then it disappears from the coupler also, and then it emerges here in qubit 2. Yeah, this is basically the last, yeah. So this is great. What is really nice about this is that it's agnostic to the coupler. So basically, if you look on resonance, the interference pattern does not change whether the coupler is in state 0 or 1. It just has to, the coupler just has to be at the end of the gate in the same state. Of course, it works a bit worse if the coupler is in state 1 because you have one more decay channel. But in principle, both work. And the last slide I want to show you is that we can actually do error mitigation. So because we have single shot readout on all of these, we know what the coupler should be at the end of the gate. It should be in the state where it started. So if the coupler started in 0, it should be in 0 at the end of the gate. So let's look at that situation, that scenario. It's this one. So if we measure 0, then we can post-select on the times when we measured 0, because we know that probably the gate worked better back then. And now just look at this interferometer right here. And compare it to the one which is not selected, post-select, right? So you can clearly see that it actually does get better, right? We get better when we select to 0. And if you look at the bottom one, you see that on resonance, actually, if we measure 1, we are almost certain that the coupling didn't work because basically everything disappears. On resonance, when we measure 1, it means that the energy went into the coupler, so it should not be here, and it's not here, and it should not be there, and it's kind of not there. I mean, it's still, you have to be really on resonance for this, so it's not perfect, but it definitely is washed out. All right, so with this, I will end. In summary, connectivity plus many degrees of freedom plus coherence, it's a big headache, right, for the entire community. So this is really a big challenge, and we have to find innovative. I think the solution is to think about interesting new ideas. Our modular architecture solves some of these problems. So it offers record-breaking isolations. It allows these parametric 2-qubit gates, but this could be implemented on any, you could deploy this on any architecture. Right? These 2-qubit gates are based on Landau, Zener, Stückelberg, Majorana, are very general. And it allows a very nice modularity, which I think it's particularly attractive to academic groups, where during a PhD, you want to sandbox and test different configurations with minimal changes to the rest of the device. So in conclusion, we need to think outside of the box, but don't forget, inside the shield. You need to shield everything. All right, so this is a picture of the group, and I just want to highlight the two main actors, Simon and Sören, who performed most of the work that I have shown you today, and I'd like to thank you for your attention.
Okay, thanks a lot. Time for questions. Okay. I think he was faster, so go. It's okay, yeah, but you have, okay, let me go. We don't have much time for questions, so let's be fair.
Thank you for the nice talk. I was interested specifically in this LZM thing which you did at the end, because we recently did an LZM in a 100-qubit Rydberg array, like many-body system. So I was wondering, so there we saw that if you increase the number of qubits, you really reduce the interference pattern, like things happen sometimes. So I was wondering, when you make it modular, would you see similar worsening of the interference pattern here due to interactions which might come into play, many-body interactions?
Yeah, I think the answer is yes, in the sense that if you add more beam splitters, right? So right now it's a very simple system where you have an array of beam splitters, and these are mirrors, and you always go beam splitter, mirror, beam splitter, mirror, beam splitter, mirror, right? Now if you add more of these objects, then you go beam splitter, beam splitter, beam splitter, mirror, beam splitter. So this becomes a difficult, it's a non-tractable, this becomes a photonics simulation, basically, right? So I think there will still be coherent interference at some points, but these points in the parameter space might be very, very tiny. So they might be washed out by noise. Right? I think that's the challenge. I don't think the points of perfect interference disappear. I think they just become very localized, and then you
we lose some patterns. That's what we found. Yeah.
Exactly. And then you just skip over them because you have finite control.
Yeah. Thank you.
Yeah. Okay, quickly. Here.
Thank you for the nice talk. So I was curious, because the coupler qubit that you use is very close in frequency to the other two qubits,
yes,
right?
Yes.
Is this to do this kind of gate? Or why was this true? Because usually it's like very separated in energy scale, no?
Yeah, so this is what helps us, right? The coupling is modulated with a huge gradient over 100 megahertz here. Right? So we go on-off in 100 megahertz. So that allows us, that means that we don't have to park too far to be off. Actually, it's worse if you go further. It actually becomes worse again because you don't benefit from this interference.
All right.
So you really want to be on this slope here. Yeah.
All right. And maybe related to this, to when you were explaining that you can measure, you can sometimes lose the excitation to the coupler. How often does this happen, or?
Yeah, I think we are still quantifying. This is work in progress. We're still quantifying the exact fidelity of this gate. So the first step is to measure 1 here and count how many times we measured 1. I don't have that number in mind right now. Yeah.
Yeah, I have a question about your readout.
Yeah.
Because you mentioned that basically your qubit and your resonator share an inductor.
Yes.
Does this mean that your coupling Hamiltonian at the end it's purely longitudinal in the qubit basis? Or
No.
So it's still energy.
It's still dispersive. Yes.
It's
still transverse, and then you work in the dispersive limit. Yes.
Okay.
Yeah.
Okay, I'm afraid we have to move on to the next speaker. So thanks a lot, Ioan, again.